Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. Today we pick up with electric circuits on page 9, and we begin with single circuits where there's a single path for current flow. The current is going to be the same in each resistor, and because of that we can write this current formula: I equals I1, it's equal to I2, and so on. We have a different voltage or energy that's lost in each resistor, but the sum of the voltage drops is equal to the voltage gained in the battery. And we can write then that V is equal to V1 plus V2 plus V3 plus for as many resistors as you have. Equivalent resistance is a single resistor that could replace the several resistors in a circuit, and we'd use a resistor formula to calculate that. As more resistors are added, the equivalent resistance increases, and to show that mathematically we'll say R equivalent equals R1 plus R2 plus R3 and so on. We have an example of a series circuit drawn over here. Here's an example of a parallel circuit. All parts are connected side by side. We have multiple current paths. So I total is equal to the sum of the currents in the individual branches of the circuit. But we have the same voltage lost in each resistor. Each resistor is effectively connected across the battery. So this formula is going to say that the voltage drop across each resistor is equal to the battery voltage. Equivalent resistance is always less than the least valued resistor, and as more resistors are added, the equivalent resistance decreases for right here. All right, up to the top of page 10, and we've got our formula here for calculating equivalent resistance in a parallel circuit. Note that we've got 1 over R equivalent equals 1 over R1 plus 1 over R2. So when you solve this, remember to take the reciprocal at the end. Conservation of charge in circuits. We could say that current entering any point in the circuit must be the same as the current exiting that point. And so here's a little example that we have over here. We have 3 amps going into a branch point. We have 5 amps going into a branch point. So the amount of charge coming in has to be equal to the amount of charge leaving. So we're going to have 8 amps exiting that branch point in the circuit. Electrical power is the rate at which work is done or energy is used, and power is a scalar quantity. It's going to be measured in watts. For our power formulas, you got P equals VI, I squared R, and V squared over R. Electrical energy is a scalar, again, quantity that measures the ability to do work, and it is the product of power and time. Power and time. The electrical energy formula is W equals PT, and notice that we've got power and time here. V times I is power times time. We have the other forms of the power equation as well. Moving on to magnetism. Permanent magnetism is caused by the unpaired spin of orbital electrons. It's important to know that it is caused by spin and not the movement of electrons. We have 2 poles, north and south. North poles of a magnet point. If you think about it for a moment, north poles of a magnet are going to point north. Again, you probably know that like poles repel and like poles attract. And the Earth is like a large magnet with a south magnetic pole located near the geographic North Pole. Magnetic fields are just regions where forces exist, and the field is the transmitter of force. Here's some things about magnetic flux lines. By definition, they exit North Poles and they enter South Poles. They are continuous, and they form closed loops. They never cross, and where flux lines are close together, the field is strong. The direction of the field is the direction that the North Pole of a compass would point in the field. And here are some magnetic field distributions. I've got them sketched over here to the left. We start at the top. I'm doing them in the same order that they're listed here. This is a bar magnet. Two like poles. I've got north poles. We can tell that because the flux lines are exiting those poles. Unlike poles, very much like the electric field, and of course the horseshoe magnet is very similar in the electric field to the parallel plates. Electromagnetic induction is generating a potential difference or a voltage when you move a conductor through a magnetic field. And we always say if the conductor cuts the flux, then a voltage will be induced. Now we're going to the top of page 11, and that's where we're going to wrap up this video. Here's a little sample of a wire moving through a magnetic field. These X's represent the magnetic field going into the page. The velocity of the wire is to the right, so we can see that the magnetic field and the velocity are perpendicular to each other, which generates a current caused by the potential difference that is perpendicular to both. If the conductor moves parallel to the field, then no potential difference is induced. And I'm not going to sketch that one, but since these lines are going into the page, if you were to move this conductor up and down parallel to those magnetic field lines, you would not get an induced potential difference, and therefore you'd get no current. So that's where we're going to stop the video, and next time we'll pick up with waves.